Hi, in this video we're gonna talk about Ohm's law, resistors, what is resistors, what kind of resistors we have in general use, and power law. And at the end of video we will gonna burn resistor that cannot handle current and power rating. So what is resistors? Resistors are components. Now in 1 minute I will show you physically. Their duty is against the current flow. They are limiting the current flow. So more resistance increase. If you increase resistance, the current ampere is dropped. Yes. So I draw this same circuit here, like equivalent circuit. It's easy to understand. I will draw such kind of drawings more after this video. So what is resistor doing inside? If you are thinking like that, imagine that there is walls in here inside of resistors, walls, and electrons want to pass through that resistors. Yes. Again, I am saying you, they are going like from, if it's plus and minus, they are going from minus side to plus. But we are thinking like conventional flow. So what they are doing, that small electrons hitting that walls, and bouncing back. Some of them pass. Some of them pass. Some bouncing back. So it's limiting the ampere. So it's limiting the quantity of electron passing through that wire in a unit time, in 1 second. If there is, for example, if there is no resistor, 10 electron passing in a second. If there is no, if there is resistor, now it's 5 electron passing, because half of it bouncing back, or more or less. But if you increase the resistance value, you are decreasing the ampere. So their main duty is limiting current flow. So in here you are seeing different type of resistor. For example, 10 ohm resistor, ceramic, 5 watt, 4 ohm resistor. There are differences. It's 10 watt, it's 10 watt, it's 5 watt, and again 10 ohm resistor, 25 watt. Some different resistor, metal film, carbon film, like that, and that small surface mount resistor. Let me show you such kind of resistor, so small. They have different shapes, types. You are seeing generally that resistors in your life, that small one in electronic circuits, and that one generally you are seeing that one like this. After that, this one, this and this one, like they are calling as power resistors. They are resisting more power, more current. So in 1926, George Simon Ohm defined that there is a relationship between voltage and current, and he defined there is ratio. He defined resistance ratio between voltage and ampere. So he defined resistance voltage divided by ampere. There is some ratio, and he called it resistance. And he gave his last name Ohm, and symbol is omega. And the main formula is here. But you are seeing every textbook everywhere like that. How can I say it? Like voltage is equal to current multiplied by resistance. It's not exactly correct, because voltage is, you can't define voltage by current and resistance, but you can describe resistance by voltage and ampere. But don't get stuck on it. Ensure that next videos we will go resistor serial connection, parallel connection. You will understand so exactly. So now let me, before I am gonna give you example. Also, I want to describe voltage in different way. It's like power. I will gonna describe voltage as power. So now I am clearing and I am gonna explain. So now we are in power. What's power consumption of circuit components or general? Well, so there is simple circuit and 1 volt and 1 amp passing through it from anything. It can be lamp, motor, resistor, anything. So if volt, if volt what? So what is volt doing? Volt creates pushing force. If 1 ampere, if 1 volt creates 1 watt power to push 1 ampere from through that component. So we can describe like that. So if we have 1.5 volt, so if we have 1.5 volt, it creates 1.5 watt to push 1 ampere per ampere. So we can describe voltage like that. So from here also you can type power is voltage multiplied by current. Now I will do 2 example. I'm deleting blank. So we have given here a simple question. 12 volt connected to 50 ohm resistor and asking what is our ampere passing through that circuit and resistor, what is, and what is the power consumption of that resistor. It's dissipating heat. Or I must draw that heat with red one, because in general people heat, yes, it's dissipating that voltage, and it's generally generate heat from current flow. So what we know, what we learned, Ohm law, yes. So in Ohm law, what we are saying, yes, we have 12 volt in here. We don't know. They are asking, and we have 50 ohms. So our ampere is 12 divided by 50. So it's equal to, also I'm doing now. Let me see. Yes. 0.24 amps. So we know already. For 0.24 amps. So what is our watt? It's power consumption of that resistor. We know here is 12 volt in that node, and here is 0 volt. So its voltage drop from that resistor is 12 volt. Yes, our voltage drop in our resistor is 12, same as here. So what is our general power law? Is power is equal to voltage multiplied by current. And you can type to current here, you can see it, you can type like that. You are derivating, you can derivate like that. So let us use that one. So our voltage drop in here is 12 volt multiplied by 0.24 amps is equal to 2.88 watt. So we know 2.88 watt. You saw on my hand there is different resistors. For example, that blue one, do you remember? It has wattage value is 0.25, as I remember. Other that wire, that metal, like green one and white one, they have 5 watt and 10 watt ratings, power ratings. Like your dryer or your washing machines, they have all that. For example, your kettle has 2000 watts. So also resistors has power ratings. So if I made that circuit from that resistor which I am choosing 50 ohm and power rating is 0.25, it will burn out. Now I'm gonna burn out. We will increase voltage physically. I will apply some voltage to certain resistor. It will go through voltage go through it, and we will gonna burn out. But before, we will do some table, and in that one I will show you by calculations. We will look physically how it comes, and in calculation how it comes, you will see. Before we will burn out resistor, I'm gonna give you one example more. It can be any part of any circuit, like, oh, it's like that, resistance here. Okay, we are just investigating some part of circuit. Okay, that part, for example, it's between A and B. Okay, so our fixed resistor over there, we know its value, 42 kilo ohms. 42 kilo, it's K, kilo ohms. What is it? For like kilobyte. You are using internet, megabyte, gigabyte, kilobyte. So 1000, 42K, 42,000 ohms. And we have here current 20 milliamp. Milli is 1 to 1000. So our amp in here is, if it's 20 milliamp, 20 times that number, it's going to 20 divided by 1000. So if you do like that, our current is 0.02. So they are asking us what is the voltage drop that here. It can be simple circuit, so that voltage, if it's simple circuit, there's a green, like damaged. If it's simple circuit, it can be also same as voltage supply voltage. If it's part of circuit, just voltage drop across the resistor. But okay, we don't know, and it's not important for us now. They are saying just between A and B. Okay, between A and B. So what is our voltage drop? So let us type Ohm's law. Here is Ohm. They are asking what is voltage between A and B. Yes, so we are doing what between voltage A and B is equal to ampere here multiplied by resistor. let me do my calculator. So it's equal to 840 volts. So high. Yes, it's so high. So we know it's volts. 840 volts. What is our heat dissipation or power consumption from that resistor? So what we know, I'm deleting here. Power is equal to voltage times ampere, or we can type anything here. It can be, we know here. We can type, if instead of voltage we are putting that one here, it can be same as like that. They are same formula, or it can be, we are just derivating three other forms from Ohm law and general, inside of general power law we are putting Ohm law. So okay, which one you want to do? Okay, let us from here do. We know, even if we don't need voltage, if we want to calculate power dissipation, just that one and that one is enough for us. We don't need that voltage when we are calculating. Also you can do from here. So I am using that one. Okay, so it is square of ampere 0.02 multiplied by our resistor. I can type K, or I can type like that. So let me do. It's 16.6 watts. It's power consumption of that resistor. Now we will gonna burn out one resistor, which that resistor that cannot handle that power rating. I will put small resistor and we will increase voltage, and we will find the critical voltage. Okay, at first we will calculate, then we will do. Okay, now I will really physically we will apply 75 ohm resistor. It has power rating, that resistor is 0.25 watt. So we will increase voltage step by step, 1, 2, 3. That I will make this photo, and I will apply the corner of video when we are doing. So when we apply 1 volt, we will read that voltage and that ampere. How I calculate this table from Ohm law, because we will not change our resistor, it will be constant. I will not remove cables and again different resistor. I will not do this one. Our resistor in our experiment will be same, so it's constant. So from Ohm law I can calculate so easily our ampere, how much current passing through it, and our wattage rating from general power law, volt multiplied by volt multiplied by current, like that. And as you see, our resistance has 0.25 watt power rating, so it will demolish, it will not do his duty, resistance will not do his duty between 4 and 5 volt, as you are seeing here, because 25 between here. So how we can calculate that critical voltage which it will fail? We know power multiplied by I. Also we can type we can also, we know Ohm law, and if we type instead of ampere, we can put, instead of ampere here, we can put volt divided by ohm. Yes, so our power formula becoming like that. So which value we want? We want which voltage it will fail. Yes, so voltage is equal to that one. Yes, in square root of power and resistance. We know our resistance. I am doing here. We know our resistance power rating, and we know our resistance is always constant. So our critical, I am saying here, critical voltage is becoming 4.33 volts. As I said, yeah, also it's so simple, between 4 and 5. So let me do that physical experiment. I will record. You will see my power supply, and we will read current and power on screen. Now let's look here. I have one resistor. Now I will show camera like that, if it can focus. Small resistor that we draw 75 ohms and 25 0.25 power rating watts. And now how I know it's 75, I can read, there is color code on it. There is strings like barcode, but there is color code like that. Let me make you visible, but now you cannot see. Okay, so I will measure with my multimeter. Resistors has no polarity, so where is plus, where is minus, no difference. There is no difference how I am measuring. I am putting my what is it, USB cable here. I am putting my as you see, I am putting my multimeter, and I put mode to resistors. Yes, and now I am measuring. There is no ideal word. It's showing like 67 ohms. So we made like 75 ohm. Okay, because there's also there's errors. They have big production errors sometimes, but it's not such kind of big deal by now. Just we are understanding concept. So there is no polarity. It's my power supply. You can see at first volt, which I will apply step by step. Will increase like that. Now it's not connected. Then there is ampere. Now it's going 6.6 volt, ampere, and wattage. There is nothing connecting by now. Nothing is connected here. Now I am dropping to 0, and every step I will stop and we will check. Now I am connecting like that. Look, just so simple circuit. Yes, plus here resistor, and minus, that current will pass from here. Now look here, I am increasing, little decrease. In 1 volt we also measured. Now it's 1 volt, 1 volt passing through, and 1 amp here, and 1 watt it can handle. I am touching, it's just like so little one. Now I am increasing to 2 volt. Little. Yes, 2 volt. In 2 volt, which we calculate 3 amps and 0.6. Look here, 0.6 watt. What's that? 0.6 watts. Yes, 3 amp, 0.6 watt at 2 volt. Now I am touching. There is just little one, not like that. Now it's 3 volts. We have in 3 volt also we calculate 0.04 amps and 0.12 amp. It's a little warmer, not hot. I am touching. I can touch, hold. Now we are going up. Now it's 4. In 4 we calculate 5 amp and yes, 0.20 and 24 watt. It's now critical and it's getting hot. A little hot. I am feeling hot. Now let me increase. What will happen? Oh, we passed our critical voltage. Our critical voltage is 4.33, but it can still handle. Yes, it's hot now, and it's 0.07 and 0.35 watts. Now I am increasing. Now still handling. We are far away from critical value. Oh, it's like really hot now. You can't hold more than 1 second. Increasing. Still increasing. Still increasing. Must burn now. I'm only feeling there is smoke. There's smoke coming through. There's smoke coming through. Maybe you are seeing the video or not, but look in here. Let me put some towel back of it. Maybe camera can focus, or black is better. Did you see how it's turning black? Now I'm increasing. Now I'm increasing. Did you see that smoke? Now you must see it, because it's 13 volt 2 watts and it's really burning now. And what will happen? It will burn and demolish. It will not conduct anymore. It will not show its characteristic. It will become like open circuit. I'm increasing. It's completely burned out. Somehow strange working. Of course it will work because it's burned, but okay, now I am stopping our experiment. I will make photo. In that photo you will see what it will be, what it was before that resistance, and what is now. It burned and completely white. So look here, our resistor. Before we applied, we go over voltage before at the beginning of our experiment. It was like that, and it burned and it turned to that shape. It can't handle it. Also it handles it handled more than it must be, but of course at the end, like in 2 watt or 3 watts, when you are watching you will spot it gives smoke so big amount, and it burned and it turned white, and that's all.